Angular force and torque in cycling are related, largely because of the angular constraint of the crank. The crank will introduce a combination of linear and angular motions into the joints. As torque is applied to the crank by the knee extensor and flexor groups during the power phase of cycling, angular momentum is created. In this concept, the rider must overcome two forces, gravity and inertia. In the early phase of the cycle, knee extensor groups produce initial torque on the crank, in particular the rectus femoris. In the knee flexors, the hamstring produces more angular force during the 45-degree to 200-degree crank positions. Crank is maintained by the constraints of the angular path of the pedal. Angular force and torque are more affected by fatigue or poor posturing on the bicycle. Crank length and saddle height are two factors affecting torque loads through the crank. As the crank length increases, the torque needed to turn the crank decreases. Conversely, shorter crank lengths require more torque to be introduced to initiate angular momentum. At higher cadences, the centripetal forces of the crank carry the revolutions, which will also decrease the muscular forces needed to overcome inertia of the crank. Common errors are related to incorrect anthropological measurements. Determination of the crank should be determined by the length of the thigh. Also, saddle height can introduce poor hip and knee angles for optimal contraction and force production. Proper positioning appears to be the best method for reducing injury. Injuries in cycling are often overuse injuries. The knee and lower back are typically the most affected. The knee is reported as an injury 23 to 50% of the time, while the lower back is reported around 46%. Too much knee flexion will increase compression forces on the patella, leading to chronic knee conditions. Decreases in saddle height or incorrect crank length can introduce excessive flexion at the knee, therefore increasing load on the patella. Lastly, handlebar distance can influence tension forces on the lower back and lead to injury. The concept power is the rate of doing work, which can't be determined without force and acceleration. Work is the product of force times distance. Distance divided by the amount of time is needed to equate speed, which power is shown by force times speed. It is all needed to have a full understanding of a movement. Energy can be transferred from a cyclist through muscle energy, potential energy, and kinetic energy. Internal work helps overcome inertia through the extremities and patterns. Potential energy is seen at the top and bottom dead centers. External work increases stored energy, while negative energy is the loss of potential energy to the gain of acceleration. The forces shown in external work are from the ground, rolling resistance, and aerodynamic forces against the body. As shown, gear size and pedal rate are important factors to address. The larger the gear size, the less energy is needed for work. Low gears are easier to pedal because of high cadences and low amount of energy. Vice versa, high gears are slower with more force being applied to produce power. Weight and bicycle geometry affect energy efficiency. The heavier the bicycle, the more energy is needed to accelerate. Fast twitch muscles seen with lower gears create less power but fatigue quickly. Slow twitch muscle fibers offer more power to rotate the gear using angular acceleration. Standing versus sitting is another factor that affects power and energy efficiency. Upper extremity kinetics and lower trunk angle transfer more energy to the lower extremities and crank arms. Common errors include non-perpendicular forces and pulling the pedal backwards instead of up and forwards. Higher pedaling cadence for novice cyclists is defective if work output isn't increased, or friction resistance is decreased, resulting in increased oxygen consumption. The best way to improve performance is to lower the cadence, use a higher gear, or use a decoupling crank to avoid dead center areas where output is minimal. When dealing with sports activities, there are two forms of energy we must consider and account for. The two forms are mechanical energy and metabolic energy. Mechanical energy is associated with objects' movement, which we will call kinetic energy, or its position, which we call potential energy. We know that velocity is an incredibly important component to kinetic energy. Relating this to cycling, we want to achieve optimal kinetic energy, therefore addressing mechanical energy. Perhaps the factor is to maximize velocity. Although mass does play a factor in energy, velocity has a far greater impact. We know from current literature that the ideal crank velocity is between 100 and 120 rotations per minute. This will produce the most optimal amount of peak power and torque on the crankshaft, thus producing work, or in this case, movement. As far as potential energy, in cycling it plays a major role. Although our video indicates a person riding a stationary bicycle, cycling often takes place in a three-dimensional environment with elevation change. As the bike moves up a hill, kinetic energy is what gets it there. However, as the cyclist rides down the hill, the rider is using potential energy. We know from exercise physiology that the more oxygen we use, the more metabolic energy we are producing. We also know that there is a reasonable relationship between heart rate reserve and oxygen consumption. To calculate heart rate reserve, we utilize the formula shown on the slide. Once we know heart rate reserve, we have an estimate of the amount of energy the athlete is using at their max ability. Knowing this, we can make a comparison of kinetic energy and percentage of heart rate reserve. This allows us to see if we can increase kinetic energy while maintaining the heart rate reserve. The law of conservation of momentum states that the momentum of a system remains unchanged unless acted on by an external force. Although cycling does not have collisions on a regular basis such as in football or rugby, they at times may occur. In recreational cycling, a little over 22% of all collisions are results of a cyclist striking a motor vehicle.